There we go.
Okay,
Got it.
I guess the recording is now in progress, guys. Okay, got it. All right, so we've got some special guest visitors today that are going to be really fun, you know, and it's in tune with what we've been talking about, you know, for the last couple of sessions with machine learning. Pierre Alexander Tremblay, who goes by PA, you can see him in the box up there. And I had a quote.
Uh-oh.
I was looking for your stuff, and
I'm afraid not.
yeah, okay,
I'm not
yeah.
responsible.
yeah. Pierre Alexander Tremblay is never quite where you expect to find him, and I'm not sure what else I can add to that. No. Seriously, he's been involved with computer research for a long time, and part of the statement is that he does a lot of different things. And typically, if you look for him, you know, being a software engineer or something like that, he's going to be playing bass because he's a very talented bass player. Plays with this amazing group called Loop. That, yeah, I know there's stuff in this really cool. And then if he's not doing that, he's working on interactive software. You know, if he's not doing that, he's working on the stuff we're going to hear about tonight, the FluCoMa. But he's on the faculty of University of Huddersfield in England, which is one of the cooler universities. Is Patrick Stewart still your?
No, sadly,
Oh.
and it's a long story of bad choices after him. But it's impossible to live up to him as a chancellor. You know,
That's
like,
true.
it's just impossible. Yeah.
He'll send you down to the planet with the red shirt on.
He used to make it so a
Yeah.
few times in discourse, and everyone was tracking.
So, yeah, and FluCoMa, they'll explain, stands for fluid corpus manipulation. It doesn't stand for what happens to you if you have a bad case of the fluid.
Yeah, I will apologize for that in the first slide. You'll see.
Right, and then we're also going to hear from his partner in crime here, Ted Moore, who's kind of known around here. He kind of hangs out at the CMC periodically. He was got his PhD at University of Chicago with one of our former guys, Sam Pluta, and has since gone on to bigger and better things, including this wonderful postdoc as part of this FluCoMa project. And yeah, I went through and like you played like virtually every space known to man, you know, Mass Mocha, National Sawdust, you know, yeah, everything. And I have your statement.
Uh-oh.
Ted's work has been described as, quote, frankly unsafe. And that was from that article on I Care If You Listen, which is kind of a, you know. So I'm going to turn it over to them and let them take you on a magical tour of, you know, your machine learning and fun AI stuff.
Something like this. Thank you. Yeah, an overview of what we'll talk about. We'll start with ideas and agendas on interdisciplinarity in general, and where you spend 2 million 5 years on a project. You need to know where you're going, because otherwise it becomes a code drain and you just follow your nose. So I will be transparent with the design criteria, and then we'll show some code and example, and then zoom back out on ideas of data flow, and that should give us about 90 minutes of pleasure, hopefully. You can interrupt if you have context questions, because we're kind of bulletproof now. We've done that talk about 35 times. So, but in various models from 2 hours to 40 hours, the workshop. So we have done various modes. So just jump in and agree or disagree, or all of the above. Maybe I should remove this. Sorry.
Yeah. I'll be monitoring the chat, guys. So if you have something you want to, you know, put in the chat, then let me relay it to them. I'll just keep an eye on it. Okay.
It's perfect. So, oops. Yay. So, what is a FluCoMa apart from an awful acronym? It's an awful acronym because you apply to a grant and you think you won't get it, so you don't care about this, and then you get it and you cannot change it. The ERC refuses that. You can change everything but the acronym. So it's a toolbox for programmatic data mining of sound banks. Don't worry about the spiel if you don't understand all these concepts. We'll go through them, but each of these words is very important. Toolbox, programmatic, data mining, and sound banks. The idea is to integrate machine listening and machine learning in Max Supercollider and pure data. And why integrating, we'll talk about that in a minute. but also just providing tools without giving knowledge is not giving real power. So sharing ways to explain musicianly to musicians, musical interests into these techniques, because there's a lot of technical articles out there and explanations, but how to find bridge for divergent thinkers and musicians and hackers to come in. And obviously, if you try to give that to people, they need a place to talk. So we've created we're trying to build a community or supporting and created a space where they can talk about these things. And that has been funded by the ERC, which is a fantastic program for individual pie in the sky research, which I was lucky enough to get, and therefore surrounded by a fantastic team of people, all much better at the subject than I am. So that was the whole point. And so the question is, as I don't really believe in the kind of hierarchic linear model of music making, where you have like the muse sending the music to a composer, who impose it on performer, who impose it on the public. I have much more dirty hands vision, maybe because I was a rap producer, maybe because I'm an improviser, maybe because I am in a studio music maker, but I believe that music is made with material and you don't necessarily know what you want, or if you think you know what you want, as you make it, you might be tempted to see, to go elsewhere with the material if you stay open enough. And therefore, there's a kind of feedback loop between making sense of the material and doing stuff with the material. And the question is, for FluCoMa, is why would we place a machine listening or machine learning in this loop? Because excellent music has been done and is still being done without machines. So, and then where and how you place the machine in that loop. So all of these were questions that keep tickling. So as the project started, hiring two fantastic postdocs, senior postdocs, so both of them exactly my age, both of them their third postdoc. So Gérard Roma, who worked on the Free Sound project, did his PhD in DSP, was the one in charge of the audio query of that. So he's coming from the proper engineering side, let's call it like this, but he's a live coder from the kind of that kind of super collider, dirty trance music, noise trance music making. And Owen Green, who's been a proper software engineer, but he's also a virtuoso of cardboard bowing, and he likes to bend machines to his will. And he's also worked in critical theory quite a lot in his very long PhD. So he brought to the table, they all were there to shake my, my assumptions in the project. And one of them was that engineers try to define software and community of practice as a one-way, like these are users of that, you know, and there's one knowledge mapping to do, which is called the user manual. But in effect, this is much more like what it looks like everything is intertwined and in feedback and very fluffy because we're humans, and everything is multidimensional and intertwined. Another idea that we really like to think is like statements to think about how we can make things happen. So we decided to do extensions, not replacement. Why? Because if musicians have got a virtuosity of maxing or super colliding or pure dataing in their music practice, in installation, and that relationship to the tool, which is their orchestra or whatever, brings interesting critical thinking. And adding what the very few bits that are missing for them to do proper machine listening or machine learning is much more interesting for me in terms of my research, which is making music with technology, not making technology. And therefore, if I ask for people to learn a new environment completely, I'm not building on their knowledge and critical thinking. I'm forcing in my workflow. So also, artifacts are your training. Now, Isotope sells you for $2,500 a suite of software that works really well, but they've choked the algorithm to make it sound good. These algorithms are fantastically powerful. They can go in every place. And as we know, like distortion or glitch, or all these examples of creative music making with what used to be an engineering error, that we need to enable this. And the more complicated the technology, the more it needs to be built in. And that's what Isotope doesn't do. They don't give you much creative license. They really show the algorithm so it works perfectly for their task. But in effect, I'm interested in the divergent use of these algorithms. And therefore, I've got to enable people to hear these artifacts and see how they sound, if we want to add that to their sound world. And finally, philosophy of technology for all. I'm sadly an evolutionist, probably because my beloved did a PhD in that. I've been corrupted, but I believe in diversity, and that's the way to make hybrids. And so we need to bring other people to the table, discussing, using, abusing the interface, because no interface is neutral. And therefore, the more people you bring early in the project, the more you have chances to create new music technology. And I come from Montreal, which we can talk about, speaking of echo chamber, the kind of acousmatic Montreal school of the 90s has, has problems to evolve out of it because it stays in its own world. But going in Europe for my PhD, teaching, having a wide, it has helped me a lot and confirmed that post-acousmatic is much more interesting than re-acousmatic, let's put it like this. So, and it's true in many different subfields. Schools are made, schools need to be challenged, and therefore we need more people to the table. So there's a few wonderful and many like mottos. So if you're making music, it's because you're human, and therefore as humaning, you're musicking. There are many ways of making music which are interesting. Even in a single person's humaning, you have various contexts for various musics. Imperfection is material and hearing is practice, very hands-on, and interface is identity. If you've never heard anyone in super colliding world telling you that it sounds better than Max or vice versa, you will see what I mean about this. And finally, one very cool idea that we thought about early in the process, the kind of idea that ability is important. The whole project was based for techno-fluent composers, which I considered myself of. And then at one point I said, maybe it's not just ability, but there are dispositions. So let's say that like you notice that it's horizontal, it's not hierarchical, but on the left-hand side, you have somebody like Robert Normando, who's a master of the DAW, can route the studio like nobody, but he's not going to code. That's not what he does. And on the other side, we have like Miller Pocket, who's PD, and he will perform once in a while, but his whole life is about thinking about how you make a software environment for musicking. We could also think of left as composerly and divergent. You don't improve on Bjork. You don't improve on Stockhausen. You do work after and you hybridize hopefully and go elsewhere. Whereas if you design environments, you can make more optimal decisions and design decisions, and they tend to be more convergent. That's a very blunt generalization, but divergent questions, convergent questions could be an interesting axis. But what I found out is that you have different levels of these techno-fluency, and it's definitely not happening like this guy. You're not just improving from left to right. You might be able to code in C++ like I was doing when I was before this project, the odd extension for Max or Super Collider. But when it's time to use it, you will revert back to your environment, or even maybe creating a plugin that you will then use in your timeline, because as a producer, I really like to play with my sound, make it sound good. And I definitely don't want to compile between the sound check and the gig. So, but that's me. I'm not saying it's better. I acknowledge that there are many dispositions, even within a single techno-fluent individual. And at given moments of your creative flow, you might want to dig deeper in converging questions or divergent questions or vision of technology or coding or producing or generating music. And you need to enable this in your workflow and in interface. So one of the consequences of that is that I saw the question of fluid corpus manipulation as an ecosystem. So on the left-hand side, you see things that you will have seen, a closed box, black boxes, Qatar doing a 2-dimensional or 3-dimensional visualization of descriptors, Audio Stellar, who does like a multi-dimension reduction. It's all free. Wakinator, which is fantastic OSC-based, like an amazing tutorial. Rebecca will be quoted a few times in the next hour. Yeah, that we saw that on So, and you have like these guys are really kind of doing something that is beautiful and closed box and agenda geared towards something. Now, it might not always fit what you want. And then before FluCoMa, you had to jump to the other side, which was, okay, I'm going to have to learn the amazing scikit-learn but I've got to learn Python. And Python is not made for real-time audio. It doesn't have the same pressure, doesn't have the same stability. Like, I don't care about latency, but I care about stable latency. And Python is not going to give you like a normal, like it's really hard to work with it. You could compile yourself Timber toolbox, but you have to go in C++. It's a bit of a pain, you know, in terms of music making. And we're not building on these wonderful languages, which have the agenda of music making built in. You know, these are made for making art in real time with technology. And they have very different agendas and visions of what the software should do. So what I thought we should do is maybe creating bridges. And therefore, this is where we stand. I think your Mac is going to die. Okay, whoops, sorry. Save. So, but putting FluCoMa in the middle, using various interfaces that those of you will code with us tomorrow, or even see a bit later, we've thought carefully, how can we make sure that you can come in FluCoMa from wherever you want and go out of FluCoMa wherever you want? And that is, again, very important in terms of like spending your development time thinking about interfacing. And you guys talk about data in this class, and thinking about the data flow of coding is also a way of thinking about data, because that's all these interfaces are incredibly biased. And they have affordances. There's a great paper that we quote. I can't remember the author. They talk about the various affordances of supercapacitor Macs and what kind of musical thinking they bring to the table, and things they make easier and things they make harder, which is a fascinating paper, which I can find the reference later. So that creates this little list of tools. So there's a bit more, which, you know, dividing your audio, splicing, decomposing it, then analyzing it, some kind of the machine listening metaphor, and then finding ways of hybridizing. I will send the slides. You don't need to, or it's going to be filmed if you're interested. And then there's all the dataset manipulations that we will talk about. But first, we have a few demos to show you the thing in action, because now it's all very beautiful, but let's see if we put our money where our mouth is. And this is now Ted's show.
I'll flip us to, I'll just do this. So yeah, so if you guys, if anybody comes to, whoever comes to the workshop tomorrow, we'll build some of these together and we'll take a much closer look. But right now I'm just going to show you this one example using a neural network, kind of to give you a sense of like how FluCoMa is put together, how these objects fit together, and sort of how we're thinking about handling data, handling neural networks. I know you guys were just looking at Recombinator and some other machine learning stuff, so we thought it'd be a good place to do the intro to the details. So what we have here, I'm going to sort of train this neural network and sort of highlight a few of the objects on the way that are central to how we're thinking about these things. Down here, is that big enough for y'all? Yeah. So down here we have these fluid data sets, and this is where we store our data sets. And we can see we have a data set for the inputs to the neural network and a data set for the outputs to the neural network. And when we add data to those data sets, we're actually using these messages here, set point, adding a point to the data set. And the data that we add actually first lives inside of a buffer. And so we have these buffers down here, input point and output point. And so for most of the sort of data work that one does in FluCoMa, this is the sort of frame that you'll be putting data through, having data sets where you're actually storing stuff, adding stuff to data sets, and then having buffers where we're actually storing our vectors or our data points when they go into and out of data sets and get processed in other ways. So you can see here, this input buffer has 2 samples and the output buffer has 10 samples. So very small buffers, the buffers that live on the MSP side of things and are just the size of the data vector that we're looking at. So the way that I'll train this neural network, I have an output space here of a synthesizer that has 10 parameters that I will need to send to the appropriate place. Yeah. Professionals. That's right.
You've done the mistakes
Been
many
around the
times.
block.
Zoom at the bottom.
Oh yeah, I'll have to give it to the Zoom guys, won't I?
It's fine. He's gonna play. Oh yeah, that's it. That's the one. I'm afraid of the volume level max now, if I may say. That's fine. It's just we catch each other. We're used to the black.
So we have here a sort of noisy, chaotic synth. It's rather difficult to predict what kind of sounds it's going to make, which is why it's a good candidate for using the neural network to control. And the way that I'll train it is I'll find some sounds that I like. So here's a vector of synthesis parameters that I want to have the neural network predict. So this is one of these output points. And I'll choose a place in my input space about where that should go. Maybe I'll put it down here. Add these two together. So I've added the two-dimensional spots right here to my input data set. I've added these vector of 10 values to my output data set. So I make a few more here. This one up here, as an example. This one up here, add an example. Down here, add an example. A little more in the middle. Okay. So now, if I look at my data sets I have over here, a data set called outputs that has all of those synthesis parameters that I stored. You can see they have these identifiers here. Example 0 has these values in the vector. And then a data set of input points here, which is just my XY position of my dots. And again, the two values here, and they range in name from example 0 to example 4. And so these data sets are totally agnostic of the neural network, right? This is just data, just a data container that we might use with the neural network here. We might use with the clustering algorithm. We might use with dimensionality reduction. We might use in various ways, but the data just lives in this data set container. If you have any questions as we do this, or things, if Pierre has any questions on that.
It's just you talked about buffers and data sets. You can save buffers obviously natively. Our data sets are saved as JSON. So everything that is stateful is JSON, so you can interface with any other data science package.
Could you upload the buffers from data outside then? Okay. That's important for the news data.
Yeah, you can. Buffers can be loaded and saved from anything.
Okay.
Data sets can be saved and recalled as JSON, but they can also be dumped as dict in Max. So you see them as dictionaries, and you can do what you want.
And they also, the data sets can also IO as buffers. So there's a from buffer where you convert a buffer into like the data in a buffer into a data set, and you convert the data in a data set into a buffer. So you can sort of do this flopping that way as well.
And if you're a super collider user, all of that can happen on the server.
Wow.
So it can be audio triggered. So it could be very quick.
So yes, so here's our data sets here. And so the way that the neural network trains is we actually just tell it, this is our neural network here, the fluid.mlp regressor for doing regression, and MLP for multi-layer perceptron, the type of neural network that is in here. And we just tell it the message fit. We tell it the data sets we want it to train with, the data set called inputs and the data set called outputs. And the neural network will know which inputs correspond to which outputs, what data points to associate, because they share the same identifier. So example 0 in the inputs should predict to example 0 in the outputs. Right? So then if we hit fit here, we can see the loss go down. I'm presuming the error, perhaps we often call it. But this is how we're seeing if the neural network is improving as it does more training, and we see this error decrease. So the neural network is learning from our data sets. And here it looks like it's pretty leveled out, so it's probably learned as much as it can.
It's a beauty. The suspense game of training a neural net.
So at some point here, we will stop our training. And over here, if I just click this, you get, yes.
So I see you also have like some attributes like activity. Are you actually designing the architecture there?
Absolutely.
Because that was something that's a bit of a black box.
Yeah.
Not only
So-
you can, oh, sorry, go ahead.
So the at hidden is going to specify the internal structure of the neural network. And here, hidden is a list. This list just has one integer in it, but we could have more integers. And the number of integers in the list is the number of hidden layers. And the integer is the number of neurons in that hidden layer.
Oh,
So we have one hidden layer of 3 neurons here.
okay.
But yes, we could specify the architecture with that.
You use it as propagation and stuff like that too.
It does it automatically.
That
when
does
you
not
fit.
happen.
Yep. So the fitting here is doing back propagation. It's making predictions, checking the error, propagating the error backwards through the network. And it's doing here it's doing 1,000 epochs of training. So it's using all 5 of my data points 1,000 times each time I hit fit. So here's
And
5,000 back propagations. Actually, it's 2,500 back propagations. But yes.
so, and all these parameters, we have a more advanced lecture explaining to musicians how to use them.
Yeah,
And they're all
some-
they're all interactive. So you can actually, as you fit, you're happy with the way it fit. You can change dynamically as it with a Q metro. As it trains, you say, "Oh, I don't like this network, so I'm just going to change the topology." We will obviously reseed, but you can literally say, "Oh, it's installing." It runs in real time, even as you query the thing. That you can like the whole thing is bulletproof. So it's been tested by savage coders like me, where the whole idea is for it to be. So you could change the network structure, or the learning rate, or the validation, the number of things you keep behind. With 5 items, you wouldn't validate it. All of these things you can learn interactively with them, and see that oops, it started. You've cleared before, I think.
Yeah.
Okay, good. So, but if you don't, some of them will force the network to change topology, therefore reseeds. But if you don't, some of them don't. The learning rate, for instance, you could be savage, go to 0.5. Or like this is going down, but at one point it will start bouncing around, as you know, and then you can lower, and you can do that programmatically in Max, checking your learning rate, and when you bounce, you lower the, et cetera, et cetera, et cetera. So this idea is to enable you to hack around that object and stop early because you don't care, because we're not doing overfitting necessarily. And so all of these things are interactive.
You're messing with it, right?
Yes, exactly. Brain surgery
That's
and
training.
talking to the person at the same time.
Yeah.
That's what they have to. Anyway, sorry.
Yes, so this is now trained to a relatively, plateaued error here. And here I just have a G gate, which now will send my position in 2D space to a buffer and then to the neural network, asking it to make a prediction from this 2D space. So that now if I move this guy, my synthesis parameters are automatically being predicted and therefore sent to the neural network. We can find our, essentially very, very similar to the 5 input points here that we had trained it on. So the points I had put in the corners and then in the middle, and of course the sort of interpolated in between spaces according to the training of the neural network. So that's often the first introductory patch that we'll build in workshops because it introduces the different pieces of the FluCoMa toolkit, the data set, the buffer IO, sort of a performative instrument introduction. And certainly it's one that we could do tomorrow if you guys some more building. Any thoughts or observations about that?
I imagine you're getting to this. It's interesting because it's similar to the basic mechanism.
Yep. Totally. Yep.
The thing the Weaponator isn't all of that until you do it. Some of the stuff with Nicola Hill with ML Star, looking at gestures.
We're not doing time series.
That's the thing.
We're not doing that. We are enabling ways of thinking about that differently than the feedback or the kind of time warping, which is bundling. Or we'll talk about it a bit later.
Okay, good. Yeah, that's I think.
One thing I would like to add is the JSON. You can save the various states of the neural net as JSON. So, and because it's a dictionary, you can make a dictionary of dictionaries and save multiple presets of space of training spaces, and it can be living in your patch and having fun. So, write or dump will give
Mhm.
you,
Wow, cool.
so you can export the state of any FluCoMa object as JSON. Therefore, manipulate them, read them first, and manipulate them.
You guys all remember Jason is the way that you were walking through the data sets that you got from websites and stuff like that. You can probably use Mark Sample Receiver's object to kind of scan through.
And Ted has done some things where he did training on scikit-learn.
Yeah, and then export the parameters, the internal parameters of the neural network and format them for the FluCoMa JSON format, and then load them up in Supercluster and run the neural network that was trained in Python.
Wow.
Wow.
The JSON IO, that's why it's lovely. Yeah. And this was actually because I had trained those neural networks and then started using the FluCoMa package, and I thought, oh, what if I get those over here? So,
Sorry.
yeah,
Is it MSE the training, the path value,
sorry, what?
the mean square error is the
Mhm.
training, is the training error path?
So it's the test error, but the test is the data set itself. Here
Like validation.
so we have validation set to 0. So we're actually not doing any validation.
Oh,
But you can change that to be a percentage between 0 and 1 of the amount of the data you want to use for validation.
can I just say that we are kind of like,
We are definitely over.
Absolutely.
but it's not a problem.
By there's a great sentence by Fibrin who says like musicians like small data is beautiful data.
Okay.
Like musicians are not doing data science necessarily. We don't care about regression to the mean. We like the fringe. Like maybe you love Celine Dion and McDonald's as burger, but personally, these are kind of the generic regression to the mean equivalent of music. And I think that I care more about the artist on the fringe. Therefore, these kind of, when your algorithm is wrong, sometimes it might be right for use of variability. So she gives example of like regret. An artist will play and will sample bits that are very heteroclites and very often on the fringe of the data, that if you were doing an arbitrary proper sampling of your data space, you would probably find 90% of it is not interesting, yet that's what the algorithm will try to converge to. So her approach is to curate the subset and play with the overfitting. You can stop the fitting earlier, like you don't need to overfit. You can stop and that's one thing that Owen does quite a lot, playing with half fittings. So you can save states, because you can dump in dictionary. You can save a fit, like I can fit in my error is 10%, I'll keep it there and try to 1% and say, oh, it's less interesting, and come back to 10, load back and continue in between and finding a fitting that fits your data. So all of that is part of your creative dance. Because in effect, what we want to do is a masterpiece of music. We don't really care if the data science is, the data science is a means to an end. We're not doing a model that needs to be studied. Because we don't have, anyway, often we don't have the horsepower to do that properly. Nor maybe the interest in my case, but that's it. So other people will have that interest. But personally, I want to see Pluto take his unwieldy instrument and curate 3 sets of space where he can actually make amazing music and make these kind of things where there's a dialogue between him and unwieldy synthesizer and then a way to wield it. So that dynamic is really interesting for me. And that's why the interface enables that.
So the next example I'm going to share with you guys, yes, is I think one that some of you have already seen. And that is this piece that I wrote during the pandemic called Quartet. And the Quartet was a remote collaboration. Oh, so the artistic hypothesis that I set out when I started this was I wanted to use programmatic data mining, so the FluCoMa toolkit, to reorganize a corpus of recorded sound according to the similarity of these sounds. So the way that I did this was this sort of workflow here that I'll outline for you. The first step was really choosing what is the corpus that I'm going to analyze and then compare for similarity. I was asked to compose a piece for the Switch ensemble, which you see here, an instrumental ensemble. And this was a remote collaboration. So I wrote about 2 minutes of music that I sent them. It was for flute, percussion, piano, and cello. And I sent the score to them. They recorded the audio and video for me and sent back these individual stems of them each performing these parts. So then I had many, many minutes of recorded audio of this music I had composed. The next thing I did to break apart this audio was nothing particularly clever. In the toolkit, there are some ways you can analyze this audio and look for, amplitude onsets or look for spectral changes and really try to intelligently break apart the sounds to try to find where things might be interesting that you might want to do more with. What I did was I just took this many minutes and broke it into slices of 100 milliseconds each. Just every 100 milliseconds made a new slice.
Oh, that was cool.
Yeah. Oh, you just wait.
Wait.
You just wait. Yeah.
It's high budget, Brad. We gotta get going. That's right.
So now I have many thousands of sound slices, all of which are 100 milliseconds each. And so the next thing I did was I analyzed each of these sound slices using some of the audio descriptors in the FluCoMa toolkit. You can see up here like spectral centroid, spectral spread, pitch, loudness. On the right here, some MFCC analyses, which is for Mel frequency capsule coefficients. And after doing all of this analysis, I had many, many values, many, many dimensions for each one of these sound slices. And too much data for me to really reason about or try to feel creative with or really know what to do with. So the next thing I did was I used an algorithm called principal component analysis to analyze the data set. And principal component analysis is able to analyze my data and find some values, some dimensions in my data set which might be redundant. So where things behave very similarly and therefore could remove some of that redundancy for me. And also able to find some dimensions or some analyses in my data set that are very noisy. And so really aren't very useful in distinguishing these points from each other, right? Essentially, it seems like the values are random and don't relate to other values in the data sets. So after using principal component analysis, I was able to reduce my data set from many, many, many dimensions down to just 11 dimensions. And principal component analysis is able to create those 11 dimensions that are going to still very well show the differences within the data set, sort of still be able to distinguish these points from each other in meaningful ways. Here we're seeing it in 2 dimensions because it's on a screen, but you could imagine each one of these sound slices have 11 values that describe it in some way. So once I had it reduced to these 11 dimensions, I then wanted to try to find a path through this 11-dimensional space that would visit each one of these sound slices just once, and also try to minimize the distance of this path, right? And this is like the classic traveling salesperson problem from computer science. The idea being touching all of these sound slices once with as short of a path as possible. And the idea here is that if I create this path through this 11-dimensional space, the sound slices that end up near to each other on this path will be near to each other because they are near to each other in this 11-dimensional space. And they're near to each other in this 11-dimensional space because they sound similar, or at least their audio analysis that I did turned out similar. So then what I did was I took this path that,
I'm sorry. So you say sound similar.
Yeah.
But am I right in thinking that what you mean is these things exhibit data characteristics that are similar to one another and that they may sound completely different?
Exactly. And that's when I describe this, it's a conceptual leap I made.
Yeah, no,
You're
I
absolutely
was
right.
curious because I thought, because I was thinking that you were headed towards T-Sting because the Kyle McDonald
That's nice.
Mannequin thing.
The what thing?
The Kyle McDonald Mannequin Google project where they took 150,000 bird recordings
Yeah,
from the
totally.
Cornell Ornithology Lab and they organized them by similarity.
Yep, totally.
And that ended up sounding similar adjacencies.
Yeah, I was
Yeah.
gonna say, I mean, the space you're describing is a bit of an anomaly, right? Where they have very similar descriptors, but they sound different. I don't think you're gonna run into that one.
Wait, say again?
Where you have similar descriptors in
Yeah.
the descriptor space, but they sound different from each other.
Right.
My sense is that that's not gonna happen that often. Am I wrong about that?
We'll talk about
we'll
that.
talk-
We'll talk about that later.
But you're right in pointing out that the assumption I'm making here is that will hold true.
Yeah, the
Right,
data
that-
similarity, sonic similarity.
Totally.
Right.
And
You'll hear it soon.
Yeah,
Oh.
and the yes, you'll hear it too. And it's also right to point out that that is like here I've only presented as a hypothesis and as an assumption. When we hear it, we'll see how true that is. Right. So then I have this path, and then I just use that path to reorganize the sound slices in time according to that path. So I get a reconstructed version of my original sounds that has all the same sound slices as the original, but reorganized according to some, analysis of similarity.
You have to say which sexy algorithm you used.
I'm going to say it next.
Sorry.
So the algorithm that I used to create that path, you can see in the upper right-hand corner there,
Sorry.
it's called UMAP, which is a cousin descendant, improvement upon TSNE. And when I did the UMAP algorithm, I went from the 11-dimensional space after the 11 principal components down to just one dimension. So I asked UMAP to find me a single dimension that would, maintain the local and global neighbor topologies. So in a moment, we'll hear this reconstructed sound file. First, on the right, I'll just tell you that this plot here is a 2-dimensional UMAP taken from the 11-dimensional space. So I did the 1-dimensional to get the time ordering, and I did a 2-dimensional UMAP here just to visualize it in 2D space. So the XY axes are not human readable in any way, but all of these points correspond to a sound slice, and hopefully their visual proximity here will relate to their sonic proximity.
What's the color?
And the color is from a k-means clustering algorithm I did in the 11-dimensional space. So I did the clustering in the 11 dimensions, and now we're seeing those clusters colorized here in the 2 dimensions, just as another way to sort of peek into that 11 dimensions a little bit and maybe get a sense of the what sort of clumping or clustering might be going on in the 11 dimensions.
I think Brad needs a repetition of this. There's many ways of looking at 11 dimensions.
Yeah, so help me. Maybe I can point it out here.
Are you gonna cloud shape it? Awesome.
2 orange red bodies.
Yeah.
This looks like what my grandson reads, a guy named Captain Under.
Yeah. I love it.
Or like the UNICEF.
Yeah.
Nice.
Oh, yeah. Sorry.
No, it's great.
fine.
I'll go find the captain of the face. I have
Yeah,
some
welcome to
nieces.
Columbia. We engage in deep topics.
Love it. Proper divergence.
So in a moment, I'll press play. And what you'll see on the right-hand side here is a black line start to zigzag around these points, connecting them all, revealing in real time the path that we're hearing. And then on the left-hand side, you'll see a video clip of the performer actually playing that sound slice. So we'll get a sort of visual representation of that reordering of the slices as well. And I think the volume is going to be correct. Yes. So that's that's what the algorithm came out with. That was when I pressed play on the results, that's what I found. Are there any observations, questions?
Why there are four?
That's a great question. So when I did the reconstruction of the sound file, I had these 100 millisecond sound slices, and I actually started them offset by only 25 milliseconds, so that they're actually we're always hearing some part of 4 different sound slices, so an overlap of 4 in the reconstruction. And so the video ended up being the case that there are 4 videos at any moment that are sort of being heard. So I chose to organize that.
The video also fed into the system.
So the video was not done with the video is not analyzed in any way or done any sort of analysis on, but the video was so this was all done in SuperCollider, and then I was sending OSC over to Open Frameworks that was rendering the video.
Come through this question. So keep all of this, and then give me a joystick that can allow me to weight the feature abstractions from the dimensionality. So like, spectral separator is driving similarity. I'm on, other features.
So because this is a dimensionality reduction algorithm, right? And UMAP is or dimensionality reduction algorithms of this nature, this iterative nature, in general take a while to compute. So it's not something that would happen in real time like that.
So that stage from the data grid that you showed to the 11 dimensions that you brought it down to, that's an optimal time activity.
Yes.
Probably have to pre-compute them and then just do some kind of class.
So
There are there are a few things you could do. We could brainstorm. There's a lot of ways of approaching that interesting problem of changing importance of proximity.
yeah.
You could also just scale, like literally, if you're doing Euclidean distance, and you could once your system is normalized, 1 is 1, and you could decide that in one set of dimensions you scale, so their distance become greater, and therefore their weight in the Euclidean distance will be
Or
distorted.
easing curves on their fall off.
Exactly.
So you'd be basically distorting the UMAP.
Which is already distorted anyway to squash. And that's why you see zigzags there. Like if it was a 1 dimension, you see just going in line. That's what it's here. But then it's 11 dimensions squashed on 2, so suddenly you see zigzags.
But you could do the 11 dimensions because they've already.
Yeah.
Yeah, totally.
Although none of them is human readable. It's a UMAC.
So the
It's a
principal
PCA, so each of them is a
that
recombination.
one, yeah. So leaning into principal component 1 or 2 wouldn't really be a human decipherable. It loses.
I mean,
There's
humans
still,
are over.
there's still like a weight factor that kind of will tell you how much of each
Totally.
initial feature you're getting with each one of the
And you
components.
could distort
Totally.
that.
So you could kind of weight
Yeah,
that.
you could literally add noise to that, literally.
Yeah.
Which is my favorite filter. Adding noise, you can add those in the bicep, just to tweak a bit of those things. So these coefficients. So you could do the same with PCA.
Yeah.
And you can do that all in real time because it's on buffers.
Exactly.
So you can literally just throw noise in your buffer, multiply it, add it to your query, and off you go. Because the interface is enabling that way.
Which would be sort of like doing a latent spacewalk, right? You have 11 principal components and you're navigating those 11 dimensions, you would get some sort of calling it a latent space is a little bit incorrect because that's a different term, but it would be that sort of a thing, right? Moving through a smaller dimensional space and accessing similar ones.
What the parts I found scientifically interesting was when you were actively moving from one object to the next.
Yeah.
And you would actually hear almost like section out. It's very cool.
Yeah, I mean, that was one of the things that was, when I heard this for the first time, I was like, whoa, that's kind of impressive.
They're like one piano concept.
Totally.
Like a bunch of this high.
Yeah. And then like a transition from from a cello harmonic to a bowed vibraphone, which is like, yeah, that makes sense. It makes sense to the data, and it also makes sense to my perceptions of like what that sound is and how it's produced. My experience of it.
And obviously UMAP had to jump at one point because there's that amount of kinship, and then at one point you've got to go to another block of kinship. At one point, it's going to organize that big jump between New York and Los Angeles, and the traveling salesman, you know. But then, oops, you fall into a locality again, which is very.
What happened down there on the left, you know, where that one
Yeah.
thing went out,
Yeah. I will say that when I so this is actually from one section of this piece. The rest of the piece has other parts using FluCoMa in different ways, and also using machine learning in different ways. And for this section, I got this result, and I used another traveling salesperson algorithm, just a more generic like traveling salesperson solver algorithm. And so I got a different ordering, a different path. So I had these two video files like this, and I actually listened through both of those and found moments and phrases and gestures that I liked and cut those out and ended up putting those in the piece strategically. So one more pass on my sort of human filter of my own aesthetic and organization of sound. But this was certainly the process for creating that raw material that then most of which found its way into the piece.
How long did it take you to compute some of this stuff? And did you do it on just your laptop?
Oh yeah, totally. Yeah, and that's a good point. You know, the FluCoMa tools are generally designed to be a personal computing laptop sized data sets, sized algorithms, sized creative process. And that's really because, you know, this is the type of user, the type of creative musician that we're interested in engaging with, right? Somebody who has fluency in Max, SuperData, Pure Data, runs things on their laptop, has a creative process that is iterative in that way with that technology, and we want to fit into that. So, you know, having something be moved to the cloud or taking 2 weeks to train or something, that's
Google Magenta.
totally, that's
First, they
cool, that's
do
cool
that
stuff.
with-
It's just a different.
It's cool, but it's also a bit boring. They do that. You've heard what they've done, you know, like the instruments are boring as hell. But what's interesting is that if we start seeding these questions now, in 10 years, when M1 technology like shared memory, shared CPU, built-in machine learning is much more mature, what they do right now on farms will be done on personal laptops, but we'll have the critical thinking that goes, if we leave to the boring people doing boring models, when the technology kicks in, we're going to be 20 years late. So if we start with what we can do right now, start thinking divergently with that technology, and where are the hinges, what are the assumptions of interface, of coding, what are like the pretense to objectivity which don't hold ground, like, you know, Google sacked their ethicists. There's not like, there is something we have to fight back on these terms of thinking about these tools as not neutral, not objective. So we need to fight with them. And then that's what musicians do well, like fight against technology. So when in 15 years, FluCoMa 3, I don't know, like something else. I don't really care about the tool set per se. I care about the ideas and the thinking a lot more. I think there's something to do with this technology, but we have to stop being demo makers and we start to be able to be engaging with the limits and the affordances of these instruments. So here we go, back to philosophy again.
I have one more little demo that I'll show.
Definitely.
Because it shows another whole section of the toolkit. So it actually shows a section of the FluCoMa toolkit that I was just using. So that's why I'm following it up with this after that video. But a section that we didn't look at on the first demo. And so what I'm going to do here is drag in a folder of sounds. And FluCoMa actually downloads with a bunch of example files that are in this folder.
It's one of the things I forgot in your introduction, like this tools.
Yeah.
They're really, really popular.
Thank you.
Yeah, so,
Can talk about the link between the his tools and FluCoMa later.
Well, that's where a lot of.
Yeah.
So I'm gonna take this folder of sound files, it's just like a bunch of test files or demo files for doing the FluCoMa examples and tutorials and this sort of stuff. So I drag them in here. And we wait a moment. We'll see a plot here in 2D space. And And these are, I'll go through the workflow briefly in just a moment, but these are the sound slices that the FluCoMa has identified, analyzed, and plotted for me. So now if I move around in the space, I can actually have access to all of the sound files. Exactly. So, and the idea here is that, you know, again, this sort of, their proximity in this two-dimensional space hopefully raise their sonic proximity. And so now I can navigate this corpus of sounds according to, you know, maybe I want to perform it with an instrument and navigate to certain sounds during performance, or use this to find similar sounds according to some sound that I'm interested in, or find groups of sounds inside the corpus that I might want to compose further with. The way that this is different from cat art is that it gives you access to all of the underlying assumptions that you have to be made, or the decisions that need to be made in order to create a plot like this.
Demo is a good soul. He's just under supported.
So
I love him.
yeah, that's okay. We say that, yeah, we say that too. So you'll notice here what's going on is I'm taking this sound file, I'm loading.
It's fine. Demo knows we love him. It's the institution that is the problem. It's not him. We know that.
So I have all these sound files that are now loaded into a buffer, one big buffer. I'm using an object called fluid.buff novelty slice, which looks through that big buffer, does a spectral analysis on it, and then looks for novelty, by which I mean distinct changes in the sound. So where is there a distinct change of some kind? And then is giving me in samples the location in that buffer at where all those changes take place. So now I have a whole bunch of sound segments that are all going to be different lengths according to the novelty of the sound in that buffer. Then I take those sound slices and I do an analysis on each of those sound slices, doing a MFCC analysis using fluid.buff MFCC, getting 13 coefficients, the first 13 MFCCs, finding, so each one of those sound slices is going to be a different length. And so we're going to have a different number of analysis frames for each of our sound slices. So in order to resolve those differences in how long the sound slices are, we actually just find the average MFCC for each of the sound slices. So if one sound slice has 8 spectral frames, we'd get 13 MFCCs times 8 frames. If another sound slice has 40 spectral or 40 FFT frames, we'd get 13 MFCCs times 40 frames. And so what we do here using fluid buff stats is we take the average of each of our MFCC values. So we end up with 13 mean MFCC values.
Not a weighted average based on amplitude or anything?
You can do a weighted average based on amplitude. We're not doing it right here, but you can pass a weights buffer to this buff stats and it'll do a weighted average based on anything actually.
Okay.
So, you know, loudness is a good thing to use. Also, another good example is using the pitch confidence output of a pitch analysis to weight your mean pitch value. So then once we have the sort of mean or the average MFCC representation for each one of these sound slices, we put it into a data set. So the same data structure we're using for our synthesis parameters and our two-dimensional space points to train the neural network, we're putting these set points into the data set here. And again, this data set is agnostic of the algorithms that will be applied to it later. So it could be, this could be used for the neural network. It could be used with a clustering algorithm. It could be used with any other sort of application. And then here we put it into UMath. And so we're taking those 13 dimensions and reducing them to 2 dimensions using the UMath algorithm here, so that then we can plot those 2 dimensions into this 2D space using, this is a FluCoMa object called fluid.plotter. And then there's one more algorithm implemented here to have this instrument run, and that is a KD tree, the fluid KD tree object, which is a type of data structure that allows for fast lookup of neighbors. And so essentially the mouse position is what I'm using to look up the nearest point of in this 2-dimensional space, so that whenever I click in space, I find the nearest point to my mouse and it plays back that slice. Any questions about that process? Pierre will talk more about some more about this a little conceptually a little bit later. Yeah, question? Oh,
Is it still the same when breaking it down to 100 millisecond segments? Or
That's-
longer this time?
they're longer this time. So in this case, the slices are all going to be a different length.
Just based on whatever the files are. in the project.
Yeah, totally.
Okay.
You could do what you want. You could literally cut it that way. You could just decide to keep where you load stuff. You can have more poly buffer. You can have all of that is
And there
supported.
are other slicers too. There's an onset, like a spectral onset slicer, an amplitude onset slicer. And this novelty slicer can look for novelty in the spectrum, can look for novelty in pitch. So if you have like a monophonic instrument playing different pitches, it can actually do a pitch analysis and then look for distinct changes in pitch.
This novelty slicer operates both within audio files and across them.
It can do in real time.
Yeah.
And it
Okay.
can do in a buffer,
Okay.
and then you can store the data where you want.
Yeah.
But the output is usually a buffer as well. So buffer in, buffer out. And this buffer out there called slices will have indices. So where in that source buffer did that algorithm detect a change? Or
Is there any way you could go in and edit the slices by hand?
not yet, but we have a visualizer that we will, that Ted will demo later.
Yeah.
Which moves those marker and then they can update.
Yeah, that's
on the to-do list.
That's on the to-do list. It's a common feature request that is on the to-do list.
Is the dot dimensionality in the plot represented?
Sorry, what?
In the back of the other picture?
Yeah.
Are all those, some of those circles are larger.
So
Oh.
there's one is larger. That is the one that is highlighted.
Ah.
Yeah. So that's the highlight. You can see there's the highlight argument here. So it's highlighting that point, but you can actually, so this is actually doing, there's a data set here called plot. That's the data set that's holding the stuff that we want to plot. And I'm just dumping that data set right into here. And so it takes the 2 dimensions of my data set plot, which is just 2 dimensions, and plots it for me. However, you can also add points one at a time by setting their X position, their Y position, their size, and their color. So if you did want to manually try to represent 4 dimensions, you could send the data in like that, and you'd have to choose sort of how you're scaling the sizes and the colors. The sort of default here is just 2-dimensional data set, dump, display.
You can also,
If you click and hold, it will just continue to play.
that's your player's decision.
Yeah, so the player is down. This is actually totally agnostic of the player. This is literally just reporting out the mouse position. Yeah, and then the mouse position is being sent to the KD tree to actually look up the nearest neighbor. So the nearest point lookup is actually not even in the plotter. That's done externally, so that it could be, because maybe you want to use a plotter to access a latent space. So you don't want the nearest point. You want to have the value, and then you can access. If there was a point here, what would that point sound like?
Yeah.
So all of that is decoupled in order to make sure that those applications are all possible.
You can also change the colors as well. You can also send classes that it will color the classes independently. It's really useful to see your k-mean logarithm, all these things.
Yeah, I'll tell you, my divergent mistake, assuming thought.
Yeah, go for it.
Wouldn't it be interesting if you were able to click to play the slice and then change the dimensionality to change the root count and points on the slice around the outside of the slice?
You can totally do that.
You can absolutely do that.
You can totally code something like that.
Because I thought Brad's question earlier implied that you couldn't change, that you couldn't edit the slice sample.
Well, that's it. I was saying do it in the data. You only go and adjust stuff by hand to make the slices. better.
Okay. Yeah.
You could even-
Composer or anything,
You could even, because it's all on your giving you access to all of this, you could click, get the nearest neighbor, know the position in the original sound file, and just use that position to just do a wider window and keep analyzing. You can analyze what you want. These objects are super quick. When you analyze just one buffer, it's like much faster than real time.
Could you shift click and make a chord?
Watch this, what you do. But you can do a few of these things. I'll show you too. Like Ted will show you Zoom.
You can zoom in,
Oh,
and so you can have access to a sub part of the data. And then you can obviously zoom back out as well. This one, that's a long slice because not much novelty. It's just that. And I think that yeah.
I continue. I just want to
The-
show.
I'm not sure about the max one here, but the super collider one does pass you the modifier keys. So if you wanted to have access, and there's a callback function about what should happen on every mouse action. So you could take that modifier key and do it your own.
I was unsure of what sonic access to the thing you use for analysis for Delta.
But yeah, in effect, you can build your own. I just want to show the multi-selection color and radius. Like KD3, again, is very good at giving you a few neighbors, and our object highlights as many as you want. So you can do a query, give me up to 30 points within a radius of 0.3. That gives you that, and you can see that it's really quick. You know, I'm browsing. This is your KD3 object. Obviously, if you give it a wider radius or a smaller radius or a smaller number, you can just check. This is the great thing about KD3. You can really query dynamically, get 2, 3 nearest neighbor, get their position in the sound files, sum their descriptors, make an average of them, query on this. Yeah, and the flutters is a full GUI in JavaScript.
So here's some color and point size and point color.
And this is just driving me nuts though.
Sorry.
So let's just show the, no, but if you show the classes, that's a good one too.
Yeah.
So you've got, oops, oh yeah, I forgot.
This
This is a bug.
is, yeah, we need to fix this bug.
Yeah, it's just a zooming, too zoomed.
Yeah.
But anyway, so you could see classes, or the k-means example will show the class. But anyway, we can play with the tool set later, but this is the idea of decoupling, again, interface.
Yeah.
If I bake in a player plotter, I impose on you what I want to do and browse. But if I give you each of these elements at the right level of granularity, you get exactly what you want from each of these objects. And this is where it links to the HERT, to the impulse response toolkit. Like when I started the project, I wanted to have a black box sound correction, you know, sweep, then do inverse filter object. And Alex Archer, who was my postdoc on this, just said, no, we'll split the task in this, you know, a max granular level, and dealing with data flow, like this class is about data, but coding as data flow, thinking about the granularity of interface is essential because you enable things by keeping it open enough. If you make it too open, then you throw people in the C++ land. Maybe that's not what this environment is good. And if you make a black box, you keep them with your assumptions. So finding that level has been incredibly time consuming, but baked in that project, part of the research.
Okay, so that brings us to this, which Pierre will talk about.
Yeah, which is a good link.
Which is a very good.
Yeah, so that workflow that you saw, talking about assumptions, I was trying to explain to, we had like 9 commission compose on the process. This is version 2.5 of the interface and the tool set. And we're designing, the guys are designing version 3 of the help files. So all of this is really important. And I was trying to explain to people the whole process. So what are assumptions that you bring to the workflow of manipulating a sound corpora or corpus? So from a bus, you know, a bunch of samples, bunch of states, bunch of sound to a corpus, there are assumptions in this concept. Then you have to do machine listening with inverted FluCoMa and music information retrieval with inverted comma. It's a metaphor in both cases. We have to remember that it's a metaphor with limits. And then once you do that, you define proximity as similarity, which is, again, very biased and not necessarily true when you have a certain question. Once you've got these points that's supposed to make sense and you can find patterns, clusters, trends, but again, you bring ideas to the table. And finally, once you've got your things that are supposed to be similar, what are you trying to do with them? Like what would be a good hybrid? And the best way I could think of, like people think of the workflow like this, you're programming from one to the other, but fundamentally something you will find at 24 will maybe make you reassess as a musician what you brought to the table as a corpus, and vice versa. What, you know, once your workflow is built, you can just change the beginning and get radically different outputs for the same questions. So I was trying to find the best metaphor, and I think I saw a double pendulum and I just said like, this is exactly the best metaphor we can think of, because you've seen a double pendulum in the past, I think. Hopefully you have. And you know, this is a simulation, but you know, the pendulum on the pendulum creates a very chaotic system. And you change just, for instance, the mass of the middle pendulum to something very heavy. And suddenly the small pendulum behaves like a normal pendulum, and the ball at the other end goes completely crazy because it's irrelevant. So changing one parameter changed the behavior of the whole system very quickly. And that was a good metaphor to explain to my composers becoming data scientists how the workflow cannot be taken for objective nor independent, which is sadly the case very much in MIR research, often very like identifying these questions, but not thinking about the ecosystem of how one changing one element changes actually everything at the end of the process. I could watch this for hours, but let's just focus on. So I'll just go through a few of these ideas, of these assumptions. But the first one is that when you bring a bunch of sound and you decide, oh yeah, this is a corpus, you bring a lot of semantic, compositional, historical taste biases to that equation. For instance, for those of you interested in the rap, we were talking about that earlier, the snare shot of D'Angelo is nearer the bass drum of AC/DC in spectrum morphology than it is to D'Angelo's bass drum. So the concept of the role, the musical role that the bass drum and the snare play in these two music is relatively similar in the grand scheme of things, yet their sonic, the spectrum morphology is quite different. So if you don't do, you can do that with machine learning. You can actually manually label stuff, but you have to think about this, because if you just go through the metaphor of machine listening, then you will struggle to find a good descriptor that will identify these things. So why and what do you bring to the table as a corpus is non-trivial and very biased, and biasing the process. So is it samples, is it synthesizer parameters, is it a musical moment, or is it just atomic segments like we just did? And you know, a violin sound is not a violin sound. If you do your Schäferian reduced listening to the violin sound, and a Pitts Bartok is very, very far from a bowed violin sound, and it much nearer like matches or snaps, or like there's other sound that are much nearer. Then once you've done that, you've got to do your famous machine listening using audio descriptors, and then you have a time series, how you deal with them. You can do some sort of statistical measures, you can split it in time, you can do bespoke decision about what you care about time. You can try to use clever algorithms, which usually fail for complicated time series. So that's why bringing your ideas to the table is very interesting. But you have to be aware that machines don't listen. They have a narrow model of a certain types of listening. Humans do very rapid, dynamic, weighted, multimodal listening. We do that all the time. Like if you are interested in machine listening as an emulation of human listening, there's a lot of cool research happening. But it's definitely not just a stream of descriptor. And what's important to your ears change within the context of your musicking. And that's very important. So I would like you to sing the pitch of this. I've got a very practical example. Can you sing the pitch? Sing. Perfect. You all fell for it. This is the blue line is what the pitch is. And you will notice that the gray bits that is noisy right there, the silence has got pitch. The silence here has got pitch. That is the pitch you sang. Good science tells you when it's right. This is the best of pitch analysis you can find. It's FFT yen. It gives you the pitch, but it also gives you a pitch confidence. So it knows when it fails. These numbers, I don't trust. This guy, I trust. This guy, I don't trust. This guy, I trust. So this is a very interesting secondary descriptor, which this is good for monophonic sound. And this will tell you, yeah, at this point, I really trust that there is a monophonic sound within the parameters I know. And this is really useful. You as human dismissed the silence, dismissed the noise, and just took the pitch material because I asked you a biased question. I tricked you. But that's what you're going to get with the machines. You do machine listening and machine querying, you're going to get exactly what you ask for. So if you ask for pitch, you're going to get pitch. No pitch or pitch, not a question. And thinking about these things. So once you've got these numbers, like computers don't perceive, you have to build in the heuristics of similarity and deciding that proximity is one. You've just shown me it's wrong. Half of you sang an octave lower, which means that in semitone, -12 is nearer than -1. And therefore your proximity, like, I'm not saying that the model never works. I'm just saying that if you don't think about it, you have a problem. And then if you bring perception and phenomenology in there, lots of nonlinearity for human perception. So all of these are very interesting to think about. And because the system will just do like a basic distance, what's going to be, even if you go like pitch versus loudness, when is 1 dB equal semitone? Because that's what you're looking for. You're looking for diagonal distance. So 1 has to equal 1. If you normalize a full range to a full range, that's another type of problem. You just consider that the full range of loudness of the violin is equivalent to its full range of pitch. Is that true perceptually? Probably not. But all of these are important to play with, and you get different results. So one idea is to play with data and care about that data and curate that data. And going back to Rebecca Fibrink, small data is good data. Big data could be a beautiful random generator too. So negotiating what you do and how you look at your data is really important, because you'll find patterns everywhere. That's roughly like you'll find patterns. An MLP will train on about everything, and it will find patterns. Doesn't mean that you can overfit on noise, you can overfit on paradoxical data. You can, like, what are you trying to find in this data? And when you find something, how does it inspire you as a musician to go challenge any of these hinges? Do you want more sound, less sound, more descriptor, less descriptor? How do you want to deal with time? Do you want to bundle time? Do you want to have one big average? Do you want to average for the attack and an average for the sustain? How do you want to play with that data? Because what you care about is musical. Is the Fibrink's quote just after? There's a great quote that she gave a talk for the project as a keynote. And there's a great talk where she explains that musicians are very good in their practice to know what they want. They're really good at providing example. Providing a model that is just mathematically accurate and consistent is really hard, but providing pairwise example is very easy. And that's why she's done, she started to try to make clever algorithms at the beginning. And she says, no, musicians were much more clever than the algorithms. So simple algorithms enabling musicians was much more potent than just clever algorithms to people who try to make data science. So that was her approach, and I find it very, very inspiring. She's a really good source of inspiration before, during, and for our field. I think we should really care about what she has to say. And finally, once you get your nearest neighbor, what are you trying to do? Like, are you trying to find a point in between these 2 points? Are you trying to find what's common? Are you trying to find what's different? Are you trying to find variations on these 2 things? What are you actually trying to do? It's quite important to think about these things, because you might think that you know what you're trying to do as you make music. And as you do it, you will have better ideas. And this is the producer in me. Like, as a pop producer, you work in team. If you are sticking to your idea, it's the best way to make the most boring thing on earth. Because serendipity is really important in research in general and in art in particular. And I think staying open and having a dialogue with the question and answer is what this enables. So that's why we are going for that level of granularity and integration. Now, am I going for the overview first, or are you going for waveform first? I think overview first.
Oh, no, waveform.
You go first.
More,
Okay, you go. You zoom out. So yeah, we were talking about visualization of data. Yes, you have a question.
Yeah, I was wondering on the previous slide, why the term exploiting the outliers?
Oh, because it's this idea of exploitation, because you do data mining. So the idea of mining, going into a pool of potential and just taking the bits that you care about. So it's nothing to do with anything pejorative in terms of politics. It's literally just you have a pool of options, and the algorithm will literally try to find what fits most of the data. So and then the outliers are the things that statistically are supposed to be considered as error or noise, but very often musicians, that's
Centering the fringe.
but that's what she does. So the idea of tacit knowledge of musicians, curating smaller data sets of interest, zooming in on these, like the zoom in on the plot is important, like looking at the whole thing and having an overview. Sometimes you really want to hone in on something. And
Say like highlight.
yeah, and when we were doing the first example, the XY, because our object is dynamic, you can do 4 points to start with. You play your space and you say, oh no, this guy should be there, you know? So you can actually just add that point and continue your training or retrain with 5 points now, the 4 corners plus that new point, and doing like the heuristic of what you're trying to find, and playing the kind of playful musicianly like direct contact with the material is baked in. That's why all these interfaces are meant to be open and iterative in your design. We want you to be able, and I want myself to be able to make sound and judge with my ears what's happening. And it might be that I make this super clever chaos generator. Okay, fine. And it's actually very bad data sign, but it makes a great sound. I'll save as, and I'll make a good tune with this. And then I will tweak it for the next iteration. And there's the next piece or the next sound design or the next question. And it might be better data science and more interesting sounds, or maybe more boring sounds. So one of the things I did in my last piece is I tried to make this crazy synthesizer a bit more predictable. So I did 10,000 points of sampling of the space. And the results were not as interesting as when I trained on 50 points that I actually cared about. So having just literally a random generator and said, good, cling, good, okay, and I created literally with MFCCs and synthesizer, curating, I think it was not even 50, it was probably 40 points, and then making a regression between machine listening and parameters of synthesizer, but literally just the points I care about. Then suddenly the musicking, the automatic audio query was much more exciting than just doing this systematic sampling of the space. So, that's what I wanted to be able to test. And, it's not science, n equals 1, it's very subjective, but the tune is much better. And I'm ready to defend that one. So that's the whole, so that's, I created a sound I couldn't create otherwise, and I didn't think about otherwise. And that's the point of what we do. Your turn.
So one thing that we usually don't spend too much time sharing or focusing on, but we thought maybe it would be interesting to share with you guys, is some of the other visualization strategies that we have in FluCoMa, because the class is sound and data sonification, visualization, sort of looking at and thinking about data. So we thought it'd be curious to have you guys look at this and maybe get your thoughts on it. So we have this object called fluid waveform, and very simply it can do this, which is show boot and actually zoom. Nice, just did it.
Wow.
Look at that. Amazing.
I didn't say anything. I'm a convert.
Yeah,
So
yeah.
After 20 something years of math.
So here we have a drum loop, which is very nice. Just visualize it. But also it integrates all of the other parts of our toolkit very fluidly. FluCoMa, right? And so here we'll do a buff amp slice analysis. Just look through the buffer, find where the amplitude slices might be, and then pass this buffer also to fluid waveform, and it'll show us where all the sound slices might be. We can very quickly iterate on some parameters in buff amp slice and identify, okay, maybe this is tweak these, and then see very quickly whether those sound slices are, jive with what you think they should be or not. We also have ways to pass in buffers of larger analyses. So if we do a fluid mel bands analysis here and get the mel band analysis of this drum loop, we can process the mel bands as an image and show essentially a mel frequency spectrogram of the drum loop here. And because that is also just a buffer of analysis here, like the mel bands, we could also do something like chroma. And so do a chroma analysis of the oboe multiphonics file that we were hearing earlier, and shows a sort of chroma representation of these different multiphonics, and be able to visually identify, which ones might be more similar or more different than others just by looking at the chroma spectrogram here. And also these are sort of interleaved and layerable, so we can do things like plot them on top of each other, and make sure what we're seeing is lining up with what we expect to see in terms of the spectral analysis, the audio waveform, and other things. It'll also plot our audio descriptors. So here's a loudness analysis through the entirety of the buffer, being shown in blue, and is normalized to the size of our window here, and we're also seeing the overlay of where the amplitude slices have been identified according to the loudness analysis. So again, sort of layering these different analyses together and just seeing how they interact and making sure that they are what we think they are or what we want them to be. It'll show a gate analysis, so simple amplitude threshold on when it's above a certain threshold and off when the loudness goes below a certain threshold, finding where those gated moments might be. And then something like this, doing a pitch analysis. This is actually the thing that Pierre was showing earlier. We're doing a pitch analysis and plotting both the, so this is the same squeaky sound file you were singing, and then showing what the pitch time series is and the pitch confidence time series. Being able to identify where in that, how much of this is confident or where those confidences are, or how they relate to the different moments of stable pitch analysis that we see.
And obviously the mapping can be done. That's good to give you ideas of mapping. So which behaves a certain way with the sound. So I really like to put sustained sound and delay. So having the pitch confidence as a driver with a threshold could decide like, okay, this scratchy stuff, I don't want to send in delay, it's gonna be a mess. But when I've got X amount of confidence above 95%, then open that gate and send it to river. You can create these interesting cross mappings, which are very simple, but incredibly potent in terms of musicianship.
And so these are all sort of the basic implementations, just passing these sound buffers, analysis buffer, spectrogram buffers into fluid waveform. There's also a few things we can do that are a little bit more dynamic and a little bit more programmatic. For instance, taking that same drum loop and using an algorithm called non-negative matrix factorization to decompose that drum loop into different sonic objects. And then plotting it something like this. You can see on top is the original. Here's the first component it has discovered, which we're hearing. It's just the hi-hat. Here's the second component, which is just the kicks. And here's the third component, which is the snare. So doing the non-negative matrix factorization to break apart those different sound objects from our mono buffer and then plot them in a way that quickly shows us which one is which, where they are, if it is again what we think it should be or what we want it to be. I think I have like 2 more examples. Same thing, but with the 3 components, different colors overlaid on each other. So we can see sort of the outline of the original waveform, but broken apart by color, the different components that the algorithm has discovered.
And because I'm obsessed by sound quality, all of these decomposition are null sonic. Sound quality. I'm obsessed by the mastering / pop producer. So all of these are null summing. So you see the exact reproduced wave right now is the sum of these 3 terms. It gives you the exact same waveform.
And then to sort of combine a few of these, we could do something, take again the scratchy sound you guys were singing, do non-negative matrix factorization on it, and then do a pitch analysis on it and be able to see the original first component, the second component, the pitch analysis, the pitch confidence for this component, the pitch analysis and the pitch confidence for this component, all in one plot, just to again eyeball it and see like, what do we have here? How might we use this? Or again, is it what we think it should be? Is it what we want it to be? So that's another piece of the toolkit that is powerful and was really came out of requests from users. Really like, I need to be able to see this feature vector. Like I need to be able to see this time series so I know what it is and what I actually have in that buffer. And then obviously being able to map that onto the waveform, onto the spectrogram, et cetera, would be very powerful. So
obviously you can scroll, you get the XY position. It's all part of the normal GUI thing.
I'm missing something fundamental here. How are you separating the components?
Well, I did the magic wand on that, didn't I?
I was thinking you're doing the thing Melodyne guy.
That's the non-negative matrix.
Yeah. So it's the algorithm called non-negative
That's a
matrix
good lead to
factorization.
that's a good lead to what I'm saying.
Michael Casey.
Yes.
Wow.
Do you want to
So-
pick that up?
Yeah,
I mean,
that's
do you want-
great. So because are you done with waveform?
Yeah, that was
Good.
all.
So
That
good.
was
I'll
the
go back to Max
examples I
now.
prepared.
So that's a good lead. The question you've asked there is a good leeway to the conclusion-y kind of vibe, which is, oh man, it is time for conclusion, eh? So what is that fluid corpus manipulation toolkit now? there is this overview in each software. I'll use Max, but that gives you an idea of what's happening. Can I close everything? Yeah. Okay. So what you just heard there is part of decomposing audio, where we've coded various ways of splitting the sound. So always, again, archetypes, signs, making like a spear in real time and in non-real time. Everything has got a buff version when it can. Transient, which is a declicker, which has and HPSS, which takes, like vertical and horizontal line as two archetypes of percussive versus pitch. All of them running in real time, and then NMF, which cannot run in real time because it needs a full spectrogram, needs time. But we have some sexy bits that goes with it. You can actually, once you've defined your spectral templates, you can run them in real time, either as filter with an object called NMF filter, or as activation in the control domain, where you can do classifying, for instance, using your bases. So NMF is really made for musician again. If I show you the L file, you've got your component number, your source, and off you go to the races, but you can seed activations, you can oversample, you can resynthesize, you literally can do everything NMF could do for you in a very dynamic way. So again, the object, and because this object is super CPU intensive, it has a blocking. So those of you who care about threading, there's a non-blocking threading option for our objects, except the dataset ones. But for the NMF, you can run this and you get so you can send a job and wait for the 10 minutes it might take, and your piece is not going to crash. But for small buffers like this, it's very efficient because it's all based on eigen under the hood, so it's doing quick enough. And then that's the original. So number 2 is my click. So I'm oversampling there. I'm asking for 5 components. All the top stuff has been put in 1, and everything else is in there. And they're obviously playing with your FFT parameters. We have access to all the FFT. You can do the window you want, the overlap you want, and the FFT you want under the hood, and therefore get all your FFT smearing under the control that you care about, because as we said earlier, artifacts are your training. So you might want that smearing, you might not want the smearing. There's even a beautiful tutorial showing you how it changes the NMF. So that's decomposition of audio, and then you can transform audio using audio transport, which makes it hybrid using what's the name of the algorithm? Optimal transport. And then NMF morph is using 2 NMFs and making cross relation between bases, which is another paper by, I can't remember whom, but it's kind of fun. You can do that in non-real time and in real time. You have the whole data suite, which we can talk about. Slicing audio, I'll come back to that. So you can cut your audio in various ways, again, real time, non-real time. And then the descriptors that we talked about, pitch, loudness, mel bands. You can change in real time the number of mel bands you're processing. That's all fun. You can have lots of pleasure with that. I've done some cool vocoder-based, mel band-based vocoding, where you change the number of things and you resynthesize. It's kind of fun. Spectral flux is in spectral shape. So spectral shape has got seven different, where are they? We lost the first page. There's a list of 7 of them. If we go on the reference, it's not finished. So this is where we're at. Version 3 is in progress. So I think buff spectral shape will have it. Let me just buff spectral shape, L file. Here we go. Saturated spread, skewness, kurtosis, roll-off, flatness, and crest. Oh, we haven't got the full flux, but you can compute it.
Yeah, you can also get it out of, there's a new object called fluid buff.
You're right.
Onset feature. Is that what it's called?
Yeah.
Fluid onset feature. And it compares subsequent spectral frames and lets you do different comparison analyses on those, and so different sort of distance metrics that will let you get something that
energy. These are all your metrics of spectral flux.
I'm really interested in that.
So that's what. Yeah, you'll have fun with this onset feature, and you also have novelty feature, which allows you to do the same kind of novelty descriptor feature, whoops, and that's all in real time, and the buff version in non-real time. So you can do it in, so that's novelty, deciding the size of your kernel and your filter. That shouldn't be a threshold. There's no threshold for this object. There we go. And you get the kind of, you can apply it in real time. No novelty now. When it stops to silence, it will be novelty. You can see that because for a spectral analysis, going from music to silence is novelty. It's not necessarily upwards, but for the onset, the onset one, it will be have onwards as novelty. You'll see that it's kind of fascinating. So these are kind of time series of heuristics of attacks, which are under our slicer. Don't save this guy. Then we've talked about that. We've talked about that. Then you get to analysis where you have the data set and a label set. You can run stats in real time and non-real time. You get more in non-real time. You can get min, median, max. You can get your 4 different like mean, standard deviation, kurtosis, and blah, 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 etc. You got a KD tree. You've got a dataset query, which is more like SQL type. And then you have normalized, standardized, and robust scale ways of like scaling your data set and to make sure that you deal with the ranges in various ways, all of which fail beautifully differently. And then you can do some regression and classification, both in MLP, neural net, a basic neural net, but still very full of potential. And you can also do it with nearest neighbor, which works really well. And finally, you've got dimension reduction. So PCA, MDS, and UMAP, 3 different levels of involvement. Unassisted clustering or semi-assisted clustering for k-means, because you can seed the means if you want. You can retrieve them, you can play with them, you can create new dimensions with the means, the distance to the various centroids. And then finally, grid, which is very exciting. And that allows me to show you, this is all cool, but if you don't know what they do, you can go in the help file, which shows you what it does. And then you can just make a grid of it, because that's what it does. But you can also go on the website where we have a reference, which is across the creative coding environment. So Max, PD, and SuperCollider share the same syntax, share the same context, and we hope the discussions of musicians using this will share across the religious divides of Mac, SuperCollider, and PD, or Mac OS versus Windows versus Linux. That's why we support them all. And that learning there is the same. So you have an original data set and you want to assign it to a grid. That's what this algorithm is doing, finding optimally the smallest distance for each of these points to respect the original shape. And we can oversample. That's not oversampling, but if I oversample, I give it a grid that is twice as many points as it needs. So you can see that it actually moves less, but it's still on a grid that you can predict, which is very useful. And finally, you can coerce an axis. So let's say that you have 2 axes, it will put everything on 2 axes. And then if you ask for 5 in the horizontal plane, you'll get 5. And if we look at this versus this, you can see that it's working really hard to optimize. So this could become like a 5-voice fader player to your corpus. That's one way of doing it. Or you can do a TED tune by asking for 1. This is 2. You can do a 2-voice TED piece, like what he did earlier with UMAP. And you can also ask for 10 horizontal examples. But one way I've used it creatively lately, or helped somebody to use it, is actually they were looking to downsample their data set. And I said, okay, you can be clever, or you can just use this. So you make a grid, and then you take every 5 points in each dimension, and then suddenly you've downsampled to something that is vaguely representative in a cheap and cheerful way with a tool set. You know,
Christ, how big is your team of people working on this? Even the web page alone is impressive to me.
2 on the web page. So the first 4 years of the project, we were 3. And the last year we've been 4.5.
Wow.
So yeah, people work too hard.
I was
But
gonna say, do you let them sleep?
I personally just give an opportunity for everyone to shine. They're really incredibly dedicated people, and that's why I don't take the credit. Like their name is everywhere. You see that my name is nowhere. It's not an accident. It's like it's a team effort. The only thing I've done, it's just, I led bands in the past. This is the model I do for my lab. It's a band. So we share decision, we share the problem, and we share the victories. I will pass on your love. I'm sure they will be happy to hear about it. We're still troubleshooting. We see the deadline coming, and we really want it to be finished. So that's why some of the hellfire that you saw earlier, not finished, is like, oh, but we have a timeline, and we hope it happens. And that's James' magic. James is really into visualization. Ted is really into like doing great tutorial. So everyone's complementing each other. And when somebody's got a strength, the other one let them shine. And it's really cooperative. There's always magic, but like as a lab dynamic, it's like a band. It feels like this, and it's really good. So I'm happy that you noticed the results. That there's a lot of love. There's another 5 months, 4.5 months left on the project to finish these, and we're on target to finish the first iteration on all of them, including code signature and going on all the distributions. So we still find bugs though, this has been gigging for 4 years now. Like the first iteration, the first gig was for 3.5 years ago. So the things is gig ready, but we still find like the odd bug and finding a way of how does that ever, the concept of finding a bug, you find it and you say, how did that ever work? Like, here we go.
My code never has
On these wise words, I think I will leave you to this and just finish with that last slide where we ask you to be our friends. Oh, where's the slide? Welcome, join us. Oh, we don't have the be our friend slide. But anyway, I'll let you drive.
We can find it really quickly.
I'm
Are
sure you
are there
will.
any questions?
Yeah, that's it. While I'm doing the questions.
Do you have a question about the general thought?
Yes.
Calling back to your line, like how interface and platform have ideology. I'm thinking about what's FluCoMa's ideology.
Ah,
I see this, I have this flat ontology assumption, how because the machine learning, in world of machine learning, they're agnostic about some objects. There's no boundary of this is the object that makes that sound. And I think it's the same thing in the digital world where you can sample in milliseconds, you can also sample in a very long time frame. And I'm thinking, what does that mean for people who want to use FluCoMa? And one thing I'm trying to make an analogy, I actually use the analogy when you're giving your online talk, is it seems to me like it's a lot of like how when a child tries to pick up language at their early stage, they're picking up this statistical patterns from the external world, trying to frame a sentence. And in linguistics, a lot of linguists think that the reason we can parse nonsense sentences, like the famous sentence was colorless green ideas curiously, like something that's grammatically correct, but it does not have semantic value. They're thinking whether using FluCoMa, that means that we're able to swap out all the timbres, all the texture of sound. Like I can say this sentence by swap out all of the phonemes, all of the sound features to something similar, but of course not human speech. And can we find something still pleasurable in that structure, in that temporal structure? Because when FluCoMa samples sound, it samples regardless of the context, right? But we never hear sound independent of context. How do we construct that context of drawing the path in this like crazy high dimension space? Seems like a real challenge. And I think that's probably an interesting, at least what I see as an interesting problem. Right?
it is a definitely interesting problem, and the openness of the interface is there to enable you to test various hypotheses. From very simple, for instance, like I care about time in replacing a drum loop. Because I come from a French spectromorphological ear training, Schäferian, I have a bias in my listening, which is the unsaid versus the sustained ADSR roughly is baked in my ear. I can decide to statistically represent sounds as from silence, define like the NADSR of 50 millisecond, 150 millisecond, and then 300 milliseconds. That's my model. I can code it myself. That's me putting on the machine listening my own semantic biases, vision of what objects are, therefore all these ontologies. And then for drums, this works really well. So how do I replace that? I can analyze my target that way. What I've done very interestingly is I've asked for 2 nearest neighbor for that replacement, where the source material was also, the target was also in the source. So I've got speech, somebody was talking, and it's one of my 50 voices who said the same thing. And on the left channel, I've queried the sentence and it's said, so you can hear the words, they make sense. But on the right channel, I've panned the second nearest neighbor for each of those. And that creates a very vocally, because we recognize it's vocal, gibberish, which has a sense of sonic similarity and gestural similarity. But if this guy is not there, if the original is not there, I have no idea. There's a contour that is very natural, but it has no textual sense. But when I add it to the other, suddenly it becomes incredibly potent poetically, which is the way I use it in the piece later. So I'm creating the question first, musically, what is happening there, what's the sense, and then I betray my process. But that's me as a composer wanting to tease somebody into listening into something that could make sense and then giving the key. Some composers will decide to start with the key, some composers, but that's where musicking is a human in the loop thing, which is very popular in machine learning, as you know, for the last 5 years, like stopping to expect the machine to do everything and keeping the human in the loop. I'm doing music with the machine, but I am definitely encoding and in charge of my biases. And if I go meta on this, me presenting you my agenda at the beginning, or the project's agenda, is one step towards transparency of this. I'm not pretending there's anything objective in there. I'm pretending these are my agendas when I build this universe. And if you disagree with those, at least I've been clear. I'm not pretending anything else. And I really welcome that discussion. You could read the Green 2018 article on our publications website. Yeah, so.
You guys are gonna send me this?
Yeah, we'll send you. So if you go there, Green is the critical theory postdoc, also C++ coder, also musician. But this article, interdisciplinary research as musical experimentation. So it's anchored into, Georgina Born critical thinking of interdisciplinarity, and also is a big, what's the technology theorist? Finberg. He's a big Finberg's fan, so there's a bit of Finberg seated in there. So you'll see, he's a very interesting character, and everything you said there resonates very much with his practice. So you might find his art, words, and thoughts interesting. If you like cardboard,
I also think,
yeah.
I think that one of the things, like Ted's example, is a fixed grid and doesn't care what the elements are on the fixed grid, right? There are other ways, like you could start that process. I think part of what he is saying is that you could start that process with a non-negative matrix factorization and have a broken out thing of a bunch of stuff that you know are like phonemes, for lack of a better word, if we're talking in the language metaphor. So then when you do your nearest neighbor, your t-SNE, your what principal component analysis, you're getting things that are whole semantic units that then you're arranging computationally, so you get adjacencies.
It's like the context is already baked in.
Yeah, so like you're saying, oh, I would like, so dumb version, 12 notes of the scale, and it extracts 12 notes of the scale, and then I can rearrange 12 notes of the scale. But if I play the scale at a particular BPM and I sample the grid at a different BPM and I get half of a note in each of my sample sets, then I get a result that has this nonsense that you are talking about, which is an exploitable feature, if you want to.
Yeah, exactly. And it's funny that you say that because Ted has done a fantastic tutorial. The learn.flucoma.org has lots of ideas. So Hans Tuchku's use 88 base NMF process in real time to create a messy polyphonic piano tracker for his piano piece. So that's one way of dealing with this. You've got like each note becomes an ontology that this algorithm is really trying to extract, and it's getting a messy sound, and it's going to try with that definition of the world generating an output, and that's creating a fantastic. It's actually a vector of description. Like
It has to be messy to be interesting.
exactly, but how do you deal with that is the next step. So just data. But what do you want from that data, and how you deal with the data is that infinite loop that I care about. But here you have, like you were talking about NMF, oops. And so there's a podcast, there are articles, sharing code on this, like in depth, but there's NMF, which seeding bases and activation with NMF, which shows you, for instance, bass, drum, snare, and hi-hat, just generating bases to start with, and then getting what NMF will spit out of you back to you will be something like this. You can generate a scale and then encode the organization of scale, knowing that in time it will be like this. You create your filters, and then suddenly you have a certain melody that will be popping out with activations that gives you some sort of pitch tracking, but from classes. And these don't need to be tempered. These don't need to be, they all need to be differentiable in time and spectrum. So there's no psychoacoustics or even human assumptions in the NMF process. It's an XY matrix that's going to try to divide, to separate components. And it comes from like visual, like you can see examples of visual objects being extracted. And that's the simplest one, but it's really powerful because there you have like each node separated. It's not perfect, you can see, but you've got some sort of reconstruction where you can decide, the loudest of them at any given moment is the most likely class, or an absolute threshold, or etc.
You know what? I mean, I already have a bunch of questions of, how do you choose your bases?
Yeah.
And things like that, but I'm not going to ask them because we have to stop.
Yeah, we do.
Now, the good news is that you guys are going to be here tomorrow. So
Yes,
if you've got additional questions, they're going to be here for like 5 hours.
but as long as you want. We start at 10 and we bring pizza and we eat, and we just, like, I've got
Free
stamina.
lunch, guys. Free lunch.
Is there any details about this online somewhere?
Yeah, it's on the front page of the CMC website. It's 10 to 12 formal, and then break for lunch, then hacking session after.
To 3 o'clock, yeah.
Okay.
And depending who's there, we can see what we want to do.
Okay,
And-
I'm going to shut down the recording. and,
Yes, thank you.
Yeah,
people online.
let's all say thank you.
Thank you.
Okay, so guys on Zoom, we're going to shut this down now. Yeah, I see some applauding there.